All right, so what we're going to be looking at now is some ratios between sides in trigonometry, the trigonometric ratios, and we talked about the special right triangles, okay? For instance, when we talked about the 45, 45, 90, we noticed that there was a relationship between the sides. For instance, if this was x, then this was x square root of, whoops, try that a little bit bigger, square root of 2. Okay, and this side was also x. Okay, so we had the same side. A 45, 45, 90 was an isosceles right triangle. Okay, now that relationship between the sides was maintained. Now what we're going to find is that the ratio between the side lengths is also a relationship. Okay, for instance, if we think of this guy as our leg, and this guy would also be a leg, and this is the hypotenuse. Okay, we could take the relationship between the sides and find that their ratios would also be consistent. Let's use x so that we can kind of show how this works. If I take the ratio of a leg divided by a leg, then what I'm really taking is the side lengths, which would be x over x. Okay, whoops, x over x. Now, in our example, it's 7 centimeters and 7 centimeters, but we want to look at this for any given right isosceles triangle. So whatever the measurement is, both of these guys are going to have the same length, so let's just use x and x. Well, what's x divided by x? Well, anything divided by itself is 1. Okay, so the ratio between the two legs of a right isosceles triangle is always going to be 1. Okay, now we can also find the ratio. They look at the leg over the hypotenuse. Okay, the ratio between the leg over the hypotenuse. Okay, now again, we're trying to keep this general because we're trying to generally state what the relationship would be for any right isosceles triangle. So if we take a leg, in our example it's 7 centimeters, but for us to keep it general, we're going to put x. And in our example, the hypotenuse is 7 square root of 2, but to keep it general, we're going to say x square root of 2. Well, again, if I take x divided by x, that's going to cancel out, and I'm going to be left with 1. Okay, so we'd have 1 in the numerator, square root of 2 in the denominator, and that will always be true between the leg over the hypotenuse. That ratio will always be true. 1 divided by the square root of 2 when I have leg divided by hypotenuse for a right isosceles triangle, 45, 45, 90. Okay? So, in our examples here, that's what they're talking about here with these ratios between the side lengths with the leg over the hypotenuse and then the leg divided by the leg here, okay? So we came out to have the same answer, and of course they approximated here. But the whole point of this is to get you guys to understand then what would the relationship between the ratios of a right triangle be for any given right triangle? Not necessarily just 45, 45, 90, not necessarily even 30, 60, 90, but for any given right triangle. What would the relationship between the sides, or between the ratio of the sides, be? Now, what we have to think of first is we have to identify a reference angle, okay? Now, when we're talking about a reference angle, we're given a right triangle, and the right angle, okay, the 90-degree angle, we're never going to have to deal with that when we're talking about the reference angle. When we're talking about the reference angle, we're talking about the other two angles, the two acute angles that add up with the 90-degree angle to form 180 degrees, okay? Now, with a reference angle, what that is, like I said, that's the acute angle of a right triangle that, I'm going to abbreviate trig. We're talking about the trigonometric ratios. Trig ratios are based off of. Okay, so when we're talking about the reference angle, okay, and like our example here with the right triangle, there are two different angles here, this guy and this guy, that could both be a reference angle depending on what we're talking about. And that's what they're saying here. If this guy here is our reference angle, then we can define what the sides would be based on that reference angle, okay? So all of this is based on what we call the reference angle. So if we call this guy the reference angle, then in our right triangle here, remember the side opposite the right angle, is always going to be the hypotenuse. So AC here is the hypotenuse. The side opposite this angle, maybe I need to use a different color, the side opposite this angle is going to be the opposite leg, okay? The opposite leg, because it's opposite our reference angle. The side that is, they say adjacent here, but trying to put it in terms that we know, the side that helps form this angle that is adjacent to our angle here, that is the adjacent leg, okay? So the side that helps form this angle here, that's going to be our adjacent leg. So AB is adjacent to our angle, BC is opposite our angle, and AC is the hypotenuse, okay? Now, if we switch things around and we choose the other guy, if we choose our other guy over here, the dot-looking guy, to be our reference angle, then things change based on that. AC still remains as our hypotenuse, but our opposite and our adjacent are going to switch, okay? So our opposite and adjacent are going to switch. The side opposite our angle is going to be our opposite leg, so AB now becomes the opposite leg. And the side that helps form our angle, the side adjacent to it, is going to be the adjacent leg. So BC is now our adjacent leg, okay? So the side that helps form our angle over here, that's going to be the adjacent leg, okay? So that's what these guys are talking about here. So then we can kind of, based off of that, write down what each one of these are. So the hypotenuse is the longest or the largest side opposite, I don't want to abbreviate there, the right angle, okay? The largest side opposite the right angle, okay? And the opposite leg is the side, you guessed it, it's in the name, opposite the reference angle. Okay, so the acute reference angle that we're focusing on, it's the side opposite of that, okay? And the adjacent leg, we could use the term adjacent, but sometimes I don't think people quite understand what that means, but we could say it's the side that is adjacent to the reference angle, but to help you understand what it is, it's the side that helps form the reference angle. Okay, so it's adjacent to it, but it kind of helps form this angle. Whoops. It kind of helps form this angle along with our hypotenuse here. So the adjacent leg and the hypotenuse form our angle here. Okay. Now, what we want to look at is, we'll get to those examples in class. What we want to kind of look at is, based on those sides, we can start to look at different types of ratios that form because of the sides. Now, so it says, look at the ratios of the sides of a 30, 60, 90 triangle. We need to identify which angles we're referring to. Okay, so in this example, this 30 degrees, that would be our reference angle. Notice the hypotenuse is opposite our right angle. The opposite leg is opposite our reference angle. And the adjacent leg helps form our angle, our reference angle here, okay? Now, based on that, they're using a 30, 60, 90, and we know that the relationships of a 30, 60, 90, my shortest leg is x, my longest leg is x times the square root of 3, and the hypotenuse is 2x. Well, based on that information, there are different ratios that we can form between the sides. If I take the opposite, which is x, over our hypotenuse, which is 2x, I can write that as the ratio opposite of opposite over hypotenuse, x over 2x. Well, again, if I divide this out, the x's would cancel, and we get 1 over 2, which is 0.5. If I take the ratio of the adjacent side to our reference angle over the hypotenuse, that would be x times the square root of 3 over 2x. Okay, well, again, x's would cancel out. We could say it's 1 times the square root of 3, which is still going to be square root of 3. So we end up with the square root of 3 over 2, which is approximately this guy. Okay, then if we use our reference angle of 30 and say I want to find the opposite side over the adjacent side, okay, we'd have x over x times the square root of 3. X's cancel out, and I'm left with 1. 1 divided by the square root of 3, which is this guy. Okay, so all we're looking at now is if I find the ratios between all the sides here, the opposite side over the hypotenuse, adjacent side over the hypotenuse, and opposite over adjacent, we end up with these figures here, okay? Well, let's see if we can find a relationship using 60 degrees as our reference angle now. So instead of 30, let's use 60 as a reference angle. Well, that changes things. Now, this guy is still the hypotenuse, 2x is still the hypotenuse. But the side opposite is now x squared root of 3, and the side adjacent is now x. Okay, the side adjacent to our angle is now x, which is what we see here. Okay, now again, following those ratios, if I take the opposite side, which is x squared root of 3, divided by our hypotenuse, which is 2x, then we have this guy. X's cancel out, and I get the square root of 3 over 2, which is this guy. Okay, if I take my adjacent side, which is x, divided by the hypotenuse, which is 2x, these guys cancel out, and I get 1, and we get 1/2. If I take the opposite side, which is x squared root of 3, divided by our adjacent side, which is x, again, our x's cancel out. We'd have 1 and 1. In this case, we just need to put 1 at the bottom. Dividing that out, we get 1.7321. Okay? Now, what they're trying to get you to see is the relationship between those. Okay? So when we had 30 degrees as our reference angle, these were our figures for the ratios. Okay? When 60 degrees was our reference angle, these were the ratios. Okay? What do you notice about the ratios? Okay? Well, these guys, notice, these first two and these first two, aren't the figures just flipped? Yeah, okay? So the opposite and adjacent divided by our hypotenuse, those figures just kind of flipped, okay? Based on what we had there. And then when we had opposite over adjacent, these two guys here, okay, the relationship between that is really down to this. In the first one, it was 1 divided by the square root of 3. In the second one, it was square root of 3 divided by 1. Those are just reciprocals of each other. So remember when we talked about reciprocals, if I just flip it, that's a reciprocal, okay? So that's where those figures came from, okay? Now, with trigonometry, okay, what we're talking about with all those ratios of sides, that's kind of what leads us to the idea of trigonometry, which is the study of the properties of triangles. In our case, we're going to be focusing on the trigonomic ratios, the sine ratio, okay, which is one of the ratios we looked at, the cosine ratio, which is one of those ratios above that we looked at, and the tangent ratio, which is another one that we looked at above. Okay, so even though we didn't give names to those ratios, we're now giving those guys names, and it's based on what we did above. Okay, so this is what it is. The sine ratio is the opposite over hypotenuse. The cosine ratio is adjacent over hypotenuse. And the tangent ratio is the opposite side divided by our adjacent side. Okay, so those ratios between the sides. Now notice, it says sine theta, cosine theta. That's what this guy is. That guy's theta. Okay, these guys are theta. And tangent theta. That represents an angle measure, like 20 degrees, 30 degrees, 40 degrees, whatever. So this is the sine of the reference angle, the cosine of this reference angle, and the tangent of this reference angle gives us its ratios. Well, that's basically what we talked about up here. When I use 30 degrees as my reference angle, in a sense, you could think of that guy as theta, whatever angle we're talking about. These are the ratios that I have, okay? Now, based on what we just talked about, this guy would be our sine, this guy would be cosine, and this guy would be tangent, okay? So the sine ratio is opposite over hypotenuse, the cosine ratio is adjacent over hypotenuse, and the tangent is opposite over adjacent. And it's based on the reference angle that we're talking about, okay? That's why it's important to know the reference angle so that we know which ratios to use here, okay? Now, a famous saying that goes with this is SOHCAHTOA. That's what that guy is. All that tells you is what the ratios are, and then how those ratios are formed. So S for sine, opposite over hypotenuse, okay? Then we have C for cosine, adjacent over hypotenuse. T for tangent, opposite over adjacent. So SOHCAHTOA, if you remember that, that will help you understand what the ratios are. SOHCAHTOA, okay? Now, we just talked about how the hypotenuse is the longest side, okay? And then it's always opposite the right angle. And then we talked about the opposite leg and the adjacent leg. And that's based on the reference angle. So for in this case, if this is our reference angle, this would be the hypotenuse. The side opposite would be BC. And the side adjacent that helps form our angle would be AB, okay? Then if this is our reference angle, this is still our hypotenuse, okay? But the side opposite would now be AB. So this is now the opposite side. And the side adjacent, which helps form our angle, is now BC. So this would be the adjacent side. Okay, so just be aware based on where a reference angle is, where your different sides are going to be. Okay, and then we'll get to that here in a sec, or we'll work on that in class. Okay, but what these side ratios allow us to do is, given whether we're talking about degree, if we're given the degree measure of our reference angle, then we can start to determine what the ratios are. For instance, and the examples we looked at with the 30 degrees, 60 degrees, and 45 degrees, and the examples that we looked at earlier, I think we did, 30 and 60. Those were the ones that we did. 30 degrees and 60 degrees on those examples that we did back here. There we go, 30 and 60 degrees. What this table allows us to do is kind of determine what those ratios would be. Well, if we look at this for 30 degrees, it says the sine, remember that's opposite over hypotenuse, gave us 0.5, just like we found. Cosine, which is adjacent over hypotenuse, gives us this guy. And tangent is opposite over adjacent, gave us this guy. Those numbers match the ratios that we found up here. Okay, for 30, there we go. So those numbers match these numbers over here, okay? And then for 60 degrees, again, same thing. Sine, opposite over hypotenuse. Cosine, we have adjacent over hypotenuse. In tangent, we have opposite over adjacent. Those numbers match these numbers for our 60 degrees up here, okay? Now, what's nice about this table is that we can look at any degree measure. For instance, we could go down to the 45 degree measure, and we can find what the sine, cosine, and tangent ratios would be. Okay, that's what this guy is you can look at any degree measure. For instance, we could look at 80 degrees, look at the sine ratio, the cosine ratio, and the tangent ratio to find those the ratio measures there. Okay, what's the relationship between the sides? Now, the table is nice. However, what we're going to work on in the next video is trying to get out of the mindset of the table and being able to find an angle or a side using these ratios and using your calculator to help us determine what a given angle might be, or what an angle we want to find would be, or a missing side would be. Okay?